Hi guys, welcome to section 9.3, separable differential equations. Yes, we did go right from 9.1 to 9.3. You're welcome to read 9.2 if you're interested. We are only going to be covering 9.1, 9.3, and 9.5 in chapter 9 for this course currently. Today we're talking about separable differential equations. Not all differential equations can be solved, but if they are of a certain form, there are certain processes to help us solve those differential equations. If we can set up a differential equation such that the derivative of the function can be written as a product of a function exclusively of x times a function exclusively of y, we call it a separable differential equation. This can be written equivalently. Well, I can divide both sides by f of y, so I can write 1 over f of y dy dx equals g of x. Now, we don't like to look at reciprocal functions, so different books use different notation, but we often call this a new function. Let's just call it h of y. Dy dx equals the function g of x. And then from here, we're going to take this differential and bring it over to this side. So we're in the sense of just multiplying both sides by the differential dx. So then we get something of the form h of y dy equals the function g of x times dx. So we have products on both the left side and the right side. Everything on the left is in terms of y. Everything on the right is in terms of x. And if we can get it into this form, then we can attempt to solve for y by integrating both sides of the equation. So let's try an example. All right, let's look at dy dx equals x times e to the y. Clearly, we have a product on the right-hand side. This would be our function of x. This would be our function of y. So I'm going to bring this over, the e to the y, over to the other side. And I'm going to get 1 over e to the y. Dy dx is equal to just x. And then I'm going to multiply both sides by dx, bring this differential over to this side. We get the function 1 over e to the y dy equals x dx. And then I'm just going to write this as e to the negative y. It's easier for me to see when we're integrating. So now we have a function of y times the differential dy equals a function of x times the differential dx. So now, once we can get it in this form, we attempt to integrate both sides. And this works nicely because both sides here integrate nicely. The antiderivative of e to the negative y dy is negative e to the negative y. And you can check that. You can use substitution, or by now I'm hoping that you see that, plus some arbitrary constant because we have indefinite integrals. But I'm going to hold off on that arbitrary constant. I'll explain in a minute. We integrate x, we get 1/2 x squared, and I'm going to put the arbitrary constant over here. We typically don't include them on both sides. If we did include one here, we're solving for y, so we would have to subtract it over to this side. And an arbitrary constant minus an arbitrary constant is still just a constant, so this can be anything. So we typically only write it on the independent variable side of the equation. All right, now we're going to move forward and solve for y here. So to solve for y, I want to isolate the exponent. I'm going to multiply both sides by -1. So e to the negative y is equal to negative 1/2 x squared minus c. All right, now here's where we get kind of a little sloppy with notation too. Not sloppy, I guess, more say just confusing. Adding an arbitrary constant is still the same as subtracting a constant, so we tend to always just write plus c. So if you wrote minus c, it wouldn't be incorrect, because when we took the derivative of minus c or the derivative of plus c, it would still just, so I'm going to cross this one off, and I'm just going to write e to the negative y equals negative 1/2 x squared plus or minus some constant, and we typically just go with the plus c throughout the whole problem. All right, so if you had minus c there, it would not be incorrect. It's just not how you're going to see it in the process in your text. Now to solve for y, to get a known out of the exponent spot, we use our logs. And because the base is e, we're going to use the natural log of the left side equals the natural log of the right side. So now we have the natural log of e to the negative y. Well, we bring the negative y out front. The natural log of e is 1. So negative y equals the natural log of negative 1/2 x squared plus c. It's very important that that plus c is absorbed inside of the log. If it's not, then that's not the solution. All right, so now we're going to solve y just by multiplying by negative 1. Negative natural log, negative 1/2 x squared plus c. So let's just go back to the original problem for a minute. Notice we had just a differential equation, no initial conditions. This is not an initial value problem, so my solution will have the arbitrary constant c in it. So this was the differential equation. I'm going to write it back down here that we just solved. We were looking for a function whose derivative was just x times e to the function itself. So we can always, I'm not going to do this with everyone, but let's just for practice, we're going to check. So we want to show that the derivative of this function is the same as this function times e to itself. So let's first work on the left side, dy dx, the derivative of the natural log of negative 1/2 x squared plus c. Well, the derivative of this, well, the negative is just going to kind of hang out. And the derivative of the natural log of anything is 1 over that anything times the derivative of what's inside. And the derivative of negative 1/2 x squared plus c is just going to be negative x. Because we bring the 2 out front, they cancel. We get negative 1x and the derivative of c. So notice here, the derivative of plus c or minus c is going to be 0, so it doesn't really matter what we call it. So let's just clean this up a little bit. Negative 1 times negative x is just x over negative 1/2 x squared plus c. So that's the left-hand side of this differential equation. Now we want to get the right-hand side to look like this. What is x times e to the y? Well, x is just x. And e, well, y, we found to be the negative natural log of negative 1/2 x squared plus c. All right, so we got to manipulate this to look like this. If it's in fact a solution, we should be able to. Now remember, we have this property of exponents that says e to the natural log of anything equals that anything. So e and natural log cancel out, but the problem is we have a negative out front here, so we use our properties of logs, and I'm going to write this as e to the natural log, so coefficients can be turned into powers. Negative 1/2 x squared plus c to the negative 1 power. Now we can apply this property. This is x, so e to the natural log of something is just that something. No, this is just x times 1 over negative 1/2 x squared plus c, which is x over negative 1/2 x squared plus c. And that's what we got up here for the derivative. So it checks. Woohoo! That was our first separable differential equation. All right, just a side note, again, like you have to be cautious with how you write answers in the sense where you may have the right answer, although it might not always look the same. So we were given this, as this is what we came up with our solution. Right? We could have seen this as written like this. So before you conclude you didn't get the answer correct, number one, you can take derivatives, and algebraically that can be tricky, but you can take the derivatives and stick it back in. So coefficients in front of logs can become powers inside of logs. So this could also be the natural log of 1 over negative 1/2 x squared plus c, right? We can write it like that. Now, even crazier, some textbooks don't like fractions and fractions, so we really could get rid of this fraction in the denominator by multiplying the numerator in the denominator by 2. And you might see the answer like this. 1 times 2 is 2. 2 times negative 1/2 x squared would be negative x squared plus, now again, here's where we get all weird, 2 times an arbitrary constant is still just an arbitrary constant. If you wrote 2c, it wouldn't be wrong, but that's not how you're going to see it in your textbook. So realize that there are different forms for the same exact answer. They all in turn will produce the same result. So when in doubt, take derivatives, check your differential equation. If you're not sure, then by all means zoom in and let's talk about it. All right, let's try another one. Let's look at this separable differential equation. This time I added the initial condition, the function, the solution evaluated at 0 equals 1. So this is an initial value problem. We are first going to solve, well, y prime, remember, when you're solving it using separation, we're going to write it as dy dx, x, y cubed, all over the square root of 1 plus x squared. All right, so the more you do, the more obvious these become. Notice that this is just x over the square root of 1 plus x squared times y cubed. So this is a function of x times a function of y. I'm going to bring the y cubed over to the left and the differential dx over to the right. I'm going to do this in one step to save time. 1 over y cubed dy equals x over the square root of 1 plus x squared dx. And I'm going to write this y to the negative 3 dy equals x over the square root of 1 plus x squared dx. And then we are going to integrate both sides. So integration skills have got to be strong. So this is just a power function. Y to the negative 3, the antiderivative is negative 1/2 y to the negative 2. We're going to wait. We're not going to put the arbitrary constant here. We're going to keep them over on the right side of the equation. Now the antiderivative of x over the square root of 1 plus x squared, you could use trig substitution here if you wanted to be really fancy, but you could also use u substitution. If we let u equal 1 plus x squared, then du would be 2 dx. And we could use substitution, and you would see that this just came out nicely to be the square root of 1 plus x squared. And I'll let you verify that, so make sure that you can do this integration plus the arbitrary constant. So negative 1/2 y squared is equal to the square root of 1 plus x squared plus the arbitrary constant. All right, so now we have to solve it for y because we're looking for the function y that satisfies both of these conditions at the top of the page. All right, so let's first get rid of that coefficient. Multiply both sides by negative 2. So y to the negative 2 is equal to negative 2 square root of 1 plus x squared minus 2c. Now again, here we come with that. I'm going to not call this minus 2c because minus 2 times an arbitrary constant is the same as just adding any arbitrary constant. I'm going to write it like this to help me solve for y. All right, so now here, in order to solve for y, I'm going to just use cross multiplication, and I'm going to get that 1 over negative 2 square root of 1 plus x squared plus c all in the denominator must equal y squared. If I multiply both sides by y squared, then divided by this chunk, this is where I would be. So now y squared is equal to, I just like what I'm solving for over on the left side, negative 2 square root of 1 plus x squared plus c, like this. All right. Now we're going to take the square root of both sides. Right. So we're going to get y is equal to the square root of, yes, this whole mess, the square root. We have square roots in square roots. And that's okay. Now be super careful here. Remember, when you take the square root of something squared, you get plus or minus. Now we're looking for just one solution to this differential equation. So here we have to take into consideration our initial condition. Is it going to be plus the square root of this whole mess, or is it going to be minus the square root of this whole mess? Well, we're going to imply the condition y of 0 equals 1. So that tells me when I put 0 into the right-hand side for x, I get 1 over negative 2, the square root of 1, plus c, and the output has to equal positive 1. So in order for the output to equal positive 1, well, the square root has to be positive. So this is not, it's not going to be the negative square root. If we changed our initial condition to y of 0 equals negative 1, then we would have negative 1 over here, and we would have chose the second option. So what I have here now as the square root of 1 over negative 2 plus c must equal 1. So we do the algebra here, and we see that c must equal 3. So therefore, my final solution is y is equal to the positive square root of 1 all over negative 2 square root of 1 plus x squared plus c. No, plus 3. Ding dong, don't do that mistake. We just solved for c. It's an initial value problem. We can't have any c's in our final result. So there we go. Again, these take lots of practice. You'll need to work on some of them on your own. Feel free to Google problems. Come zoom in. Let's solve some problems together. All right, let's look at this guy. So we have dy dx equals x minus y. Looks pretty simple. So we want to know, let me see. Here's my function of x. Here's my function of y. The problem is we're subtracting f of x from f of y. We need my function of x times my function of y. So can I make it look like that? Well, I clearly can bring f of y over to the other side. I can say dy dx plus y equals x. But if we try to integrate, we never have the differential plus the function. If I try to multiply both sides by dx, make sure we do it on both sides, right? I would get dy plus y dx equals x dx. That's going to cause a problem. So no matter what we do, we're not going to be able to separate this. So this is not a separable equation. So it's not solvable by this method. So we have to come across other methods, or we'll have to find other methods to solve this type of differential equation. But this section just talks about separable equations. So if it's not separable, we are not going to solve it right now. All right, let's check this guy. It looks very similar to the last one, except this time the difference is in the exponent. Now, be careful here because this difference can be turned into a product. Notice that this is just dy dx is equal to e to the x, e to the negative y. So if we